Welcome to NQuest Physics students. In this class, we are going to learn about the work, energy and power. First we start with the work. First of all, we have to understand what is the work is. By the application of the force, if a body gets displaced, work is said to be done. Okay, by the application of the force, if a body gets displaced, the displacement must be along the direction of the applied force. Then only we call it as the work done. Okay students, it can be understandable very easily. Let's take a coordinate axis system. Okay students, let's say R and it is the force. Displacement vector. Locate a point. It is A and its position is R1 bar. And a force is applied on this particle. It's the particle. And the path traced by the particle is this. And it reached another position. Let's say it is R2 bar. It is the actual path traced by the particle. If you say it is R bar, okay, it is the point B, then R can be had as R2 minus R1 and applied force is F bar. Then we have to find out the work done. I told you work done is the product of the force and displacement. Actually, it is the dot product of the two vectors. Work done can be written as W is equal to F bar dot R bar. As you know that the dot product of the two vectors yields AB cos theta. In the same way, if you multiply the two vectors, you get if it is FR cos theta. Okay students, W is equal to FR cos theta, or if you say the R is displacement and W is equal to Fs cos theta. Okay students, here W is a scalar quantity. As you know that the dot product of the two vectors always yield the scalar, and work has the units of, what are the units? Joule. Okay students, or simply we can write it as J. In SI system it is. In CGS it is erg, and the two are related as 1 joule is equal to 10 to the power of 7 erg. Okay students, and the dimensional formula is equal to M1 L2 T inverse 2. And you have to remember that the same is that units go with the energy also. Okay, energy and work done have the same units. Let's now see the types of work. We are talking about the different types of work students. Okay, as we know that work done can be had as W is equal to Fs cos theta, where F is the constant force students. Okay students, F is the constant force and S is the displacement. And what are the types of work? Actually, works are of three types students. One is the positive, second is negative, and the third is zero work. Okay students, work is classified into three types. One is the positive work, second is the negative work, and third is the zero work. First we have to discuss when the work is said to be positive. A simple case, students. If the displacement and as well as the applied force are acting along the same line, we call it as the positive work. Let's take is a smooth surface and a body is lying over. Okay, students. And we applied a force in this direction. It's the line of application of the force. Okay, students. Here, what did happen? Because of this force, this body get displaced and it reached this position. Let's say it is A as the B, the line of action, and this is the displacement of the body. Here see, the direction of the displacement and as well as the force are along, or they are along the same direction. Then use the formula. We know that W is equal to Fs cos theta. Here the force and as well as the displacement both are acting along the same line. That means they are parallel to each other. And you know that if the two lines are parallel, the angle between them is equal to 0. Then we can write it as W is equal to Fs into cos 0. As you know that cos 0 is equal to 1. What then is equal to Fs into 1, that is equal to Fs. Okay, students. Here this work is the positive. That means what? Displacement and as well as force applied are acting the same direction. Or you can represent the same thing. One more diagram. Let's say it's the same body. This time I'm applying the force in this way. It's a constant force which is acting on the body. Okay. And the body, imagine it get displaced to this. Here it is the displacement of the body. Okay. Then in this case the force is here is parallel to the horizontal, but it's making a certain angle with that. In such cases you have to resolve the force into components. It's the direction of the force and it is the theta. Obviously it is F cos theta and it is F sin theta. F sin theta is balancing with the normal reaction, and F cos theta is responsible for the motion of the body. The same result we yield. W is equal to F cos theta into displacement. Yes. What then is equal to Fs cos theta. Okay. Yes, see this. Here it depends upon the angle. Let's say this angle is equal to 45 degree. Then what we get? Fs by root 2. Okay. Fs by 2 root 2. Okay, students, by using what's that? This method also you can find out the amount of force acting on a body. And you have to remember that here work done is said to be positive. Work done is said to be positive when theta is, okay, simply you can write theta is less than 90 degree. Means what? Acute angle. If the angle is acute, we call it as the positive work. Okay, students, let's say the negative work. We have so many examples for the negative work. Okay, students, it's the same surface, but this time it is the rough surface, has a friction, coefficient of friction of mu, and a body is lying over. Okay, students. Then we applied a force in this way. Then automatically opposing force will act in this direction. Okay, students. Here the body is moving in this direction and force is acting in opposite direction. It is the displacement of the body. Here work done by the frictional force is negative here. Work done by the frictional force is negative. See this? Frictional force is acting in this way and displacement is this. Okay, students? Then you can write it is weight of the body and is the normal reaction. Then we have to go with that the same principle what we use it here. Work done. This time we are finding the work done by the, what is that, frictional force. Frictional force multiplied with the displacement. Okay, students. And you can write W is equal to Fs cos theta. Okay, students, see this? Displacement and force are acting in opposite direction. Then theta might be equal to 180. Work done is equal to Fs into cos 180. As you know that cos 180 is equal to 0. Then work done is equal to minus Fs. Okay, students, if you write the magnitudes, you can write W is equal to, you know that F is equal to mu n or it is equal to mu mg. Then W is equal to mu mg into S negative. Is the work done by the frictional force. Work done by the frictional force is negative. And we can take one more example, students. See, a body is kept over the surface, okay, and we are lifting the body up, okay. The displacement is in upward direction. Now we are finding the work done by the gravitational force. As you know that gravitational force always works vertically downwards. Okay, we are using the same principle there. Work done is equal to gravitational force multiplied with the displacement. Then we can get W is equal to gravitational force times to the displacement into cos theta. If you watch it carefully, theta is at 180 degree here. Okay, students. Then you know that cos 180 is equal to minus 1 minus Fg into S. This is one more example for the negative work. It is the work done by the gravitational force, but not the work done by the applied force. If you apply the force here and the displacement and force are in the same direction, in this case the work done by the applied force is positive and work done by the gravitational force is negative. Here what would you understand here? If the theta is greater than 90 degree, work is negative. Means what? The theta is obtuse. Okay, students. Let's take one more case, and the thing which is left is zero work. Okay. What is the zero work? If the displacement and the force are in right angles with each other, then we call it as the zero work. Let's say it is a circle Okay, students, it has a radius of r and the particle is moving in circular path. It is the force acting, and the particle started from here, traveled and came back to the particle A again, then the displacement is equal to 0. Then we have the equation W is equal to Fs cos theta, that is F into 0 into, no need of theta here, that is 0. Okay students, if displacement is 0 or if the force and displacement are in right angles, then we can say, what's that? Work done is equal to 0. And we have a classical example for this. That's where I try to tell. Here what is that? A person carrying some load on his head and moving along a straight road is not doing any work. Okay, a person carrying some load. He is the person. Okay, he is carrying some load on his back. Okay, moving along the straight road is the displacement. His carrying load means what? The force is applied here. He's carrying, he's holding. Then the angle between the two is equal to 90 degree. And take the same. W is equal to Fs cos 90. As you know that cos 90 is equal to 0. Work done is equal to Fs into 0 is equal to 0. Okay students. Here in this way you can define the work in different ways. Work can be classified as positive work, negative work, and as well as the zero work. Okay, if the point of application of the force and displacement are in same direction, we call it as the positive work. Then the negative. What is that? Force and as well as the displacement must act in opposite directions. The best example is work done by the frictional force. When a body is moving over a surface, displacement and frictional force are acting in opposite direction. And also I told you the work done by the gravitational force on the body is the negative and 0. If the displacement and force vector are in mutually perpendicular directions, the work done is 0. And as well as the body which is moving in a circular path came back to the same point, then work done is also equal to 0. These are the different types of work, students. Okay students, now we are going to learn about work done by a variable force. Till now we learnt about the work done by the students. Till now we learnt about the work done by the constant force. Now we have to know about the work done by the variable force. Okay students, let's say there is a coordinate axis system and is the x-axis, we are taking displacement there, and it's the force. Okay, how we have to find the work done by the variable force? Let's say is the path traced by the particle. Okay students, let's locate a point here, and I have 1, 1, 1, 1. Different points I got. Okay. This position, this particle, this position, say it is O, is at a distance of x1 from the origin, and I am taking a stretch here. Okay students. Okay. This stretch has a thickness of dx. In this way, I divided the entire path into number of stretches of thickness dx. Okay, it is A, it is B, C, so on. I am taking it as the sum C, D, E, F, G, H, I. Okay, students. And the distances are x2, x3, x4, xi up to. Okay, students. Then we have to find out the work done by the variable force. The work done by the variable force is nothing but the area under the curve F into x. Let's say it is F1 and we have a point F2, and see it is F3 and it is F4 and so on, F5 and so on. Then work done can be had as W is equal to, actually dW you have to take, is equal to F into dx. Okay, the force is variable. Okay, students, I am taking the limits from x1 to x2. F into dx, it is the variable force. Then I can write it as work done, integration of dW is equal to W, then x1 to x2 into F into dx. Okay, students, by using this relation you can find out the amount of work done by a variable force in graphical method. Okay, students, that means what? The area, this is the area, total area under fx graph gives the amount of work done. Let's do one little example. Okay, let's see this. The graph is shown in this way. Okay, students, it's the origin, the displacement is the force, let's say it is the 10 Newton, it is 5 meter and it is some 8 meter. Okay, we have to find out the amount of work done from 0 to 8. The displacement is from 0 to 8, and we have to take the area of the shaded part. Let's say it is A1 and it is the area of the triangle A2, and just we have to add them. Work done is equal to area under fx curve, this area 0 to 5 into 10. Okay, say it is WA1 is equal to 5 into 10, 50. Okay, Newton meter. And say this, for this A2 is equal to half into base 3 into height is 10 to 1s to 5s, 15 Newton meter. Then the total work done is equal to WA1 plus WA2, that is 50 plus 15, 65 Newton meter, or we call it as the joule. Okay, students, in this way you can find out the work done by the variable force. And one more example we are taking. See, the similar graph is given here. Okay, see the students, 0, say 5, 10, and it is 15, and it is 10, and it is 5. Then we have to find out the work done. It is very simple. See, you have to take the area 1 is the area 2 and it is the area 3. Okay, students, here for this part WA1, what you get is a triangle half into 5 into 10. Okay, it's 24 5 joule, and WA2 is equal to 5 to 10. 5 into 10. 5 into 10 is equal to 50 joule. And third, WA3 is equal to half into 5 into 5. It is 25 by 2. 12.5 joule. The total work done, okay, is equal to WA1 plus WA2 minus WA3 students. Remember this. Then it is 25 plus 50 minus 12.5. It is 75 minus 12.5. It is 62.5 joule. In this way, you can calculate the area. Okay, students, I hope you understood what is the work done, how to calculate the work done by a constant force, and how to calculate the work done by a variable force. The best example is the area under force and displacement graph.